It's my true pleasure and honor to introduce our next speaker. My fifth grade French teacher, I'm sure, would be very disappointed with my pronunciation of your name. Professor Guilleminot?
Yeah, it's good.
Okay, close enough.
Yeah.
Will be speaking to us about stochastic modeling for model ensembles, from physics-based to data-driven surrogates. Thank you very much, and we welcome our speaker.
All right, so mic seems to be working. I'd like to thank the organizers for the kind invitation. I have to say that I'm going to deliver more like a traditional UQ presentation, but I will have some machine learning context into it as well. I'd like to acknowledge my collaborators, Ariana, Jeannie, and Senu. They are students at Duke, and Rudy Gillen, who was here until, I think, last year, for the application to operator inference. Okay, so this is the outline of the presentation. I will start with motivation for the work. I have to say that I'm extremely happy to present amongst the last, which is something that usually we are trying to avoid. But a lot of the examples that I would give you to motivate this work are really relevant to the discussions we had from previous talks. And I will go through technical developments and show you the numerical application. So just to set the stage in terms of notation and what we're going to do in particular if you are not UQ persons. So we're going to assume that we have like a deterministic model Y function of P. P is going to be typically like input parameter in your PD. F is a forward map, and Y is the output. And so basically when you do UQ, I mean, you have essentially two types of settings you can be interested in. One is the so-called parametric setting, where essentially P is stochastic, could be infinite dimensional, like a random field, could be like finite dimensional, random vector. And then you have the P is stochastic, it's in blue. F, I'm going to keep it deterministic. And then it's going to, you're interested in, for instance, propagating the uncertainties onto Y. Or if you are more like an inverse problem guy, you're going to get observations on Y and trying to get the distribution of P. And then there is this operator setting where essentially F is going to be stochastic and this is something I'm going to write like this. So some sort of encoding form, encoded form of F is going to have a distribution pi. And then in this case, I'm going to keep P deterministic and likewise, Y is going to be stochastic. You can obviously combine those two things, but here in this particular talk, we're going to focus on the second setting. So to keep things simple, I'm just going to keep my parameters deterministic. So I'm going to show you a couple of examples of why this is actually relevant. The first, and you will understand the connection with the talk before. The first example is when you are trying to do molecular dynamics, and when you are trying to do molecular dynamics in the old ways, you would you need to define the force fields or the interatomic potentials, and they are not uniquely defined. So what you're going to do is that you're going to, for instance, go to the NIST database, and the NIST database is going to give you for different chemical species the potential that you have to use, and you're going to use that in LAMMPS and just run your simulation. Well, it turns out that if you open this NIST database for many, many species, you don't have one potential. You're going to have 3, 5, or 10. Okay? And the question is, which potential should I use? So just to give you a particular example, if you take like a simple graphene sheet and you just have like this harmonic excitation, and you select sort of typical potentials which are used for graphene, this is an example of the displacement you're going to get for a particular atom if you are going like through the Morse potential, the Tersov potential, the Erebo potential, or the LCBOP. And I don't know if you can see that, but the difference is huge. This one is almost 2. This one is almost 4. Okay. Now, still connected to the previous talk, we can say, well, no, we're going to get rid of that. We're going to get rid of the old ways of doing this. We're going to use machine learning potentials. Yeah, you can do that, but machine learning potentials are not going to solve everything, and you need to be extremely careful about the way you're going to use it. You're going to use them. So this is an example we are doing with people working on solid-state batteries. So this is diffusion of ions in energy materials. And so we take like a DFT data set, and we take a bunch of potentials, we just train them to the same accuracy, and then you run your diffusion simulation. And This is basically the mean square displacement of this sodium atom for two particular potential, the NEP and the MNIP potential. And again, you see that you have significant discrepancy in it. Now, let me clarify the fact that here is not like we are training here and we are extrapolating here. This is not the case. We are training on a data set, right? And then we are just using those two potentials to sort of make that prediction. And even if you keep NEP, which is a neural network-based potential, and you just change the seed, you're going to have exactly the same discrepancy. And that's something that is very documented in the literature. Okay? Now, there are obviously ways to bring this down, like if you know how to better train or if you build better potentials, but that's not something that I'm going to discuss today, and that's definitely not where the state of the art is right now. Another example, we have seen a lot of things like this today, working a lot with the Duke Hospital. And so when you are trying to do digital health simulations, those are real patient-specific geometries. This is a brain interface that we use to do TMS simulations. So TMS are used to treat brain disorders, like deep depressions, for instance. This is something that you would use in the middle for cardiovascular simulations. And this is a rib cage from, I don't know if you can see that, but this is someone who had a fall and broke like 7 ribs. And we are trying to essentially design biodegradable materials that would essentially promote bone healing inside this structure. So whenever you're going to do forward simulation on that, you need to select the functional form that you're going to use in your nonlinear finite element simulations. And I think a lot of people have been discussing this. Michael Sachs yesterday, I think, and likewise if you are using machine learning potentials. And now, because I'm in the Oden Institute, I'm going to this is the application I'm gonna show you today. When you are using this for operator inference, and you essentially need to define the way your model is going to be trained. And so what I would like you to see here, that if you can just ignore those lines, but just look at the colored line, those are the predictions that you're gonna get when you just change the way you train your operator inference. And likewise here, you see that you have discrepancy based on the model that you are dealing with. Now, in this particular setting, I want to emphasize that people might say, well, the difference is very small, and so why do we care about that? Here, it's all about the robustness of the learning technique. Okay, if you had 200% discrepancy here, we would do something else. We would just work on the inference context. Okay, and I will get back to this particular example later on. So in terms of the positioning of the research, for those of you, again, who are not a UQ person, the state of the art in UQ is extremely rich to capture parametric uncertainties, right? So you get like some input measure, and you are pushing forward the measure to some quantities of interest. You can go all the way back. Omar Gaddaz gave a presentation yesterday, typically in the Hilbert space setting. So George has been, leading the way in that field, and for like 30 years, we sort of know how to do that. Now, if you think about how you do that in the same way for model from uncertainties, the state of the art is way more limited, and you have like some key challenges I'm gonna discuss today. The first challenge is how do we encode the model, basically, because that's a functional form, so it's not easy to do. How do we ensure that the model we are randomizing makes sense in terms of computations, and how do we do inference? I just would like to clarify that I'm not going to deal with model correction. So my point is that I have discrepancy between data and the prediction, and I'm going to put a GP or something like this to sort of bridge the gap between those two things. This is not the focus on this presentation. So to clarify this, all of the examples I gave you can be cast in this setting where you have a family of model candidates, okay, and you have to deal with them, okay. So there are a couple of things you can do with this. One common approach is essentially model averaging. That is that you're going to run your prediction for all of your models, and you're just going to take the weighted prediction across all of your predictions. Which is obviously sort of a very crude approximation, right? It's like if you do parametric uncertainties, it's like sampling viscosity or Young's modulus 10 times, doing the propagation, just taking an average. I think it's fair to say that it's not really the state of the art in 2025. Or you could try to do model selection. Let's say I have a data set, I have a family of model candidates, and likewise here, because being at the Oden Institute, you can do model selection based on model plausibility that was pioneered by Tinsley Oden about 10 years ago. But basically, when you do that, the outcome is going to be sort of deterministic in some ways, right? So you know that you have some samples of your models, but you don't know exactly what to do with them. So the goal of this work is to develop a stochastic approach to deal with this. So I'm going to go through the methodological developments. So the way we do this, we're going to start with a reduced order representation. I'm just going to give you two examples which are relevant to what I'm going to show later on. One is when you are dealing with standard linear subspace /POD method, where you're going to use like a representation like equation 1, where essentially the parameterization phi here is going to be, in this case, the V. And then in some cases, this POD method is not sufficient. Depending on the spectrum. So you need to add some nonlinear enrichment, which is something you can write in a fairly generic form, like in equation 2. And n is usually like a nonlinear enrichment term that in this case, in our case, would be like a polynomial enrichment term, but that could be like a neural net, for instance. And so the goal is to randomize the projection basis as a way to encode the action of the operator. Okay. So this is something that had been discussed by Suaz and Farhat in 2019. Okay, so how do we do that? So to set up the notation, so this bold phi is essentially the stochastic version of phi. I'm going to be sort of heavy on notation, but the notation should be absolutely clear. So anything bold is going to be stochastic, non-bold is going to be deterministic. So if you look at the constraint that you're going to satisfy, it's a projection basis, so that belongs to the Stiefel manifold. In many cases, you have to satisfy some sort of some form of linear constraints. This is number 2. A typical example are Dirichlet boundary conditions on the boundary. And something we would like to do, we don't have to do it, but in terms of statistical inference, we would like to constrain the Fréchet mean on the manifold. Just to position the perturbations. So the combination of 1 and 2 are defining an admissible set that I'm going to denote with this fancy notation, this S notation. So to enter those constraints, the typical way of doing this is to work on the tangent space. If you are familiar with reduced order modeling and parameterized PDs, this is the usual way of doing this, and we do that because essentially it's easier to do things on the tangent space based on the mathematical structure. So when you do that, the first step you need to do is that you are living on a manifold, and you need to project on the flat space, on the tangent space. And so there are many ways of doing this. There are tons of books on how to do it. So you have this projection operator P, okay? And you have this retraction operator. So P takes you from the manifold to the tangent space, and R is a retraction operator that goes the other way around. And in this work, we are using Riemannian logarithm and Riemannian exponential, and there are very good reasons for why we do that. And the only thing and I'm happy to elaborate on that, but the point I want to make is that there are many ways to do that with very important consequences on how you do inference, how do you do the propagation, and so on. And in particular, in the initial formulation that Suaz and Farhat had, they were using like a polar decomposition to project. And because of this, and because of this second constraint, they ended up with a probabilistic model that works, but that has thousands of parameters, and that's just extremely complicated to do, to calibrate, and to propagate as well. So to build the model, we build on two propositions. They kind of look formal, but are pretty straightforward. And the idea is as follows. If you're on the manifold, okay, and all of you have a point on the manifold that satisfies your constraint number 2, and the base point also satisfies that constraint. If you project this guy onto the tangent space, that guy satisfies the linear constraint, okay? This is the first one. The second one, which is almost too good to be true, is that it goes the other way around, okay? And that is only true if you are using a iterative approximation to those two projection and retraction algorithms. If you do something else, you just hope for the best. You cannot really prove that. Now, I hope you see where I'm going to go. If you combine those two things, the fundamental idea is that if I have a collection of models, each model is going to be associated with a projection basis. Okay? What I can do, I'm going to call those points anchor points. What I'm going to do is that I'm going to assume that I have a base point that is going to be like a global reducer of basis satisfying that constraints. Then based on the combination of those two propositions, I know that basically if I retract a linear combination of those projections, that will automatically satisfy my linear constraints. So regardless of what I do, when I'm using my reducer modeling, I know that my constraints will be satisfied. Okay? There is something that is also interesting is that if you select those p sub i's, those coefficients onto the tangent, so this guy lives on the tangent space, okay? Then you can show that the convex combination yields points that belong to the convex hull on the manifold, right? So if you think about it, you have anchor points, okay? And you do this trick, and then whenever you're going to retract back, your points will belong to the convex set defined by your models, which I think is a nice technical result. So how do we enforce that we have a convex combination? It's straightforward. I just kept it for just in case you are not, again, like a UQ person. But basically, if you want to define a convex combination, you can just consider constraints 6 and 7 and use information theory, and they will tell you that this P is essentially a Dirichlet distribution. Okay? So using information theory, this is the representation we're going to use. Okay? So you have your collection of model is going to give you a collection of anchor points, like those guys. Okay? And you know how you need to sample onto the tangent space to define models which belong to the convex envelope of models that define your data set. Okay? And I will show you how it looks like qualitatively in the application. How am I doing in time?
10 minutes.
Okay, perfect. Okay, so this is a summary. Okay, so that's very straightforward, just very like a few lines of coding if you're interested in that. Now there is something else which I think is pretty simple but also very elegant. I like to work with things which are well defined, and in particular, remember what we are doing. So what we are doing is that we are building a measure for the projection basis, but we want those perturbations to be localized somehow on the manifold. And the idea is that if I have a collection of models, I have my collection of projection bases, I can define a global reducer of basis that I get by just concatenating all of my snapshots. This is sort of somewhere in between, like in the middle of my anchor points. And what I would like to do is that I would like my perturbations to be around this guy. So this guy is somehow seeing all of the models, right? Does that make sense? And so it turns out that if you do the math, it's like a 1 page, 3/4 of a page. With a Dirichlet distribution, you can show that you know exactly how you need to define your concentration parameter in your Dirichlet distribution so that your perturbation is going to enforce that constraint. And I will show you how it looks like in practice. You will see that. And that's a straightforward MATLAB-type quadratic programming problem that you can solve very easily. And you can also look at the conditioning of this and seeing, like, for instance, are my model closed? Because if your models are closed, you're going to affect the conditioning of all of this. But I think there is benefit in doing this because the model is very easy to calibrate. Now let me show you how it works in the context of operator inference. So I guess most of you in the room should be familiar with this. I'm not going to spend too much time on this, but you have this representation that is defining the mapping between the physical state space and the reduced order state space. And in this paper by co-authored by Rudy you are using this nonlinear enrichment term, but I want to emphasize that all of the stuff that I'm presenting would work if you go the Charbel-Farhat way, where the second term would be a neural net in a paper with Yvon Madé in France. And then you are, in this case, you are learning the latent space dynamics using that framework, and so basically you have this reduced order equation, and you are fitting those coefficients by solving like a least square problem. So again, the point is really not to discuss that, and again, I believe that most of you are familiar with this. And so the goal in this work is really to see, well, once I decide on a training scenario, each training scenario is going to give me one model, okay? And what I want to quantify is the robustness of my prediction with respect to that, okay? So again, I'm not expecting huge variations, but I just want to make things more robust, right? And this is something that Karen was referring to yesterday. So it's more like UQ for a learning task, if you will. So to proceed, we're going to use the probabilistic model I have shown you before to randomize the concatenation of the low frequency mode and the one that are affecting the nonlinear enrichment term. And then we're going to use like a goal-oriented definition of the base point, because in this case, the base point is not clearly defined. And I will show you how it looks like. But basically what we do is that we are running a lot of training scenarios, okay? And then we do like a Riemannian k-mean clustering to sort of identify the best number of clusters describing this on the manifold. And then we are going to localize the anchor point associated with the center of mass on this cluster. And then I'm going to take the snapshot of associated with those anchor points, and I'm going to use that to compute the base point. Okay. To show how it works, we're going to use like a very standard prototypical problem that had been used in the group as well. So I'm not going to comment on this that much. We are using like a 2D Navier-Stokes equation, and you have the usual setting, and the Reynolds number is going to be in that range. So this is how it looks like. So first of all, we are using like this data collection. So we have like 200 snapshots. This is based on the discretization. This is the size of the input. Those reduced dimensions are based on like a standard convergence criterion. And so this is a cluster analysis. So this is my Stiefel manifold, and this is a cluster analysis. So we have like a bunch of training scenarios, and the clustering analysis will tell us, well, in this particular case, we have 3 clusters, and they will allow us to identify the anchor points we are going to use to randomize the projection basis. In this case, it turned out that the anchor points are identified by these combinations of training parameters, just to give you a sense of how it looks like in practice. And this is how sampling looks like. So actually, I should switch the figure, but what you should really look into is the figure on the right. So what you see is, so those are, just to remind you that those are, we are basically randomizing projection basis on that space. So that's not something you can actually look into. But so we need to use like a reduction technique to do that. So in this case, we are using spectral embedding, but we had similar results with like, PacMap or whatever you want to use to visualize that. So that's, you are taking your big matrix on the Stiefel manifold and just crushing you in like a 2D space. So that's good to keep in mind when you are visualizing those things. But basically, this, you see the anchor points. And what you see here is that those are the additional samples that sort of belong to the convex set, although I want to emphasize that this is a projection. But basically, this is how it looks like. And here you have the global basis, and this is, in this case, the Fréchet mean. But if you increase the number of samples, the Fréchet mean is going to get even more closer to that. So this is for phi. So this is a concatenation of V sub R and V bar. And now if you sort of split the matrix into 2, this is how they would look like. But basically, the results about the convexity in the hull is in that space, not on those spaces. But I think it's still interesting to see how they look like. And then once you have this, you can look at, you can do some uncertainty propagation, and you can look at whatever is interest. So here you have like the mean velocity magnitude, the coefficient of variation for the velocity magnitude, and this is the width of the confidence interval at different time instances. And what this is telling you is that this is quantifying the impact of my training strategy on my operator inference prediction. Okay, and here you can basically see like, well, based on the combination of my inference technique and my training scenario, this is where I have the most localized uncertainties. Okay, and then you can use that to refine the analysis. So I'm almost done. So just to summarize, we presented like a generic approach to do the quantification of model form uncertainties. The well-posedness is ensured with probability 1. You have like a low-dimensional parameterization. It's easy to implement, easy to calibrate, and it really endures the learning or the prediction method with a statistical measure of robustness. That really opened up like a lot of other works. So if you're interested in that, we work the original paper, the first one. The second one is when you are trying to do molecular dynamics in statistical ensembles. So you have basically coupled equation for the control algorithm. This is a collaboration with Rémi Dengreville in Sandia. We also work with coupled nonlinear PDEs for phase field for fracture, something that Emma was referring to yesterday. ML potential, the last one, and the last paper is basically the one that I've been showing. I just wanted to show the faces of my team of warriors. So Ariana, Jenny, Senu, and Rudy, who looks very serious on this one. But and I would like to acknowledge the financial support of NSF and Aero for this. With that, I'm done. Thank you.
Again, we have time for one quick question. I know that Adrian has been burning to ask a question the whole time.
Thank you for the talk. I have a question similar to what Manuel has been asking to other speakers, and sort of where do you see the future for this, and maybe if you can comment a little bit on the intersection of this and the newest machine learning and AI tools. Yeah, how do you see that?
Well, emerging? I mean, I don't think I'm the most, so on the UQ side of things, I think there is still a lot of work to be done in terms of building comprehensive, efficient framework to capture model form uncertainties and to propagate them. Like a lot of things are based, for instance, on Monte Carlo solvers. With this method, what is interesting is that you sort of finite dimensionalize everything, and it introduces like a partitioning in the probabilistic space, and you can use like collocation method. I think we are using what George has been developing 10 years ago. They have a paper on how do you, if you have like a partitioning in the probability space, you can design efficient algorithm to propagate with PC. I didn't show you the results, but we have a paper that will come out. So you have like a lot of things going on. And when it comes to connection with machine learning is not like a huge part of really what we do. We do that, but not that much. But I think it's fair to say, and perhaps Jordan, Karen can step in, but I think UQ for machine learning, improving robustness, is definitely something that people are working on. I'm not super original on that, but I'm pretty sure. I mean, I think there have been a lot of ML for UQ, just like going faster. But I think UQ for like inference methods is still lacking. Yeah, that's the best answer I could give.
Thank you so much. Appreciate it. One more round of applause, please.